Okay, so keeping on this theme with Spearman's rank correlation coefficient, that is your first example of something that's called a non-parametric test. Okay, because it's not making any parametric assumption about the population. We're just ranking things. All right. What I did actually is the first example I want to show you has to do with the sex ratio. So I went to Wikipedia, and I know that some of you say, oh, you can't go to Wikipedia. But anyway, I did. And here it is. And so what did I see here is that I saw these three statements. That the CIA estimates that the current worldwide sex ratio at birth is 107 boys to 100 girls. So that's the CIA fact book. Then the Times of India said that they gave the ratio for 2010, for 2010, and for 2011, and there they were. I think there's something wrong here because let me put them all on the same scale, 1,000 males. So I think in 3 years that's a huge disparity. But anyway, it doesn't matter. Let's go with that. The point I wanted to make with this was that, oh, look, they're still talking about sex ratio. We seem to be stuck on this theme for many years, eons. But then I looked at this and said, wait a minute, what do we got here? Everybody understands what's stated here. I mean, it was a standard newspaper that wasn't trying to obfuscate anything. Everybody understands what you mean by 935 females to 1,000 males. Everybody understands 984 to 1,000. But what are we talking about here? We're talking about odds. And people say to me, oh, I don't know odds. I know probability, but I don't know odds. This is odds. Anybody can understand odds. Okay, but because you prefer probability, let me put it back into probability statements. So 107 over 207 is 0.5169. Probability male, 0.5040. So if you prefer to think of probabilities instead of odds, there they are. But the point I wanted to make with this is that it is still of interest today. Actually, I know they were worried about ultrasound. But anyway, that's another story. But this is still of interest today. Why I brought this up is because John Arbuthnot, there he is, handsome fellow, he lived in the age of enlightenment. It must have been a very exciting time to live then. But anyway, what he did was he also looked at this. But let me tell you a little bit about him, because he was also known for designing John Bull. So there's John Bull, and John Bull is sort of the British version of Uncle Sam. Actually, we should say Uncle Sam is the American version of John Bull because there's precedence. But you see, there's a poster from the First World War doing the same thing. You know, Uncle Sam wants you, except here it's who's absent? Is it you? But anyway, so that's John Arbuthnot. He was actually a physician to the Queen. But what he did was he looked at precisely this. He looked at the sex ratio at birth. And here's his claim. And that's why we're looking at it. He's saying divine providence, not chance, governs the sex ratio at birth. So he wrote this paper, and it was in the Philosophical Transactions. And look at that, in 1710. He was way ahead of his time. Way ahead of his time. He was measuring something about people. As I said before, at that time, you didn't apply numbers to people. And he did. But also, what's intriguing about this is he used statistics. So this is one of the very first hypothesis tests we have in the literature. This is one of the very first ones. And intriguingly enough, it's using statistics to prove that there is a God. All right? So he's saying this is divine providence. It's not chance. It's divine providence. Now, why is he saying this? He's saying this because he looked at the christenings for 82 years. And then every single one of those years, there were more boys christened than girls. So there were more boys than girls. So there has to be a God. But anyway, getting back to statistics, he says, what's the probability? Suppose the probability of a boy is 0.5. To him, that's chance. It's 0.5, flipping a coin. Okay? So there's chance flipping a coin to decide the sex of the baby. And what's the probability that for 82 years, you flip a coin. For every baby born, you flip a coin. What is the probability that for 82 years you'll have more boys than girls? And the answer is that, 1 over however many zeros that is. So he's saying this, it's 0.5 to the 82. So that's the independence assumption, which is quite valid, I guess, going from year to year. It should be independent. And that, he said, therefore, from whence it follows that it is art, not chance, that governs. Now, why chance had to be exactly 0.5 and not 0.505 or whatever it is, 503, whatever, I don't know. But anyway, there it is. That is the first hypothesis test that we've been able to come up with that was formally tested this way. The other one I mentioned, of course, was with the astrology stuff that Neumann did. But anyway, so there it is. Now, what did he do? Putting this in modern lingo, what he did was, okay, here, let me show it to you by example. Here are 13 pairs, and there's matching, and what we're doing is matching somebody with cystic fibrosis, matched according to age, sex, height, and weight with someone who doesn't have cystic fibrosis, who's healthy. And looking at the resting energy expenditure. So here is the first match, the first pair. And now if we do what Arbuthnot did, is we look and see pair by pair, we look and we see the differences, all right? And all Arbuthnot did was look at the sign. So here's a negative one, here's a negative one, all the rest are positive. So if we look at the signs, we've got 11 positive signs and 2 negative signs. And if we test our hypothesis that this difference is just as likely to be positive as negative, in other words, that median is 0, then we can ask the question, how often do you do a study with 13 signs and get only 2 negatives? Okay, so that is what is called the sign test. And what we can do is we can set up the statistic like this and do a normal approximation, or we can use the binomial. It doesn't matter. In this case, we get that the p-value is 0.012 approximately, but we can put it into Stata, and Stata will do the sign test for us, and there it is, sign test. And we see that the p-value is 0.0225. So we would reject the null hypothesis. Now, the sign test is not very powerful. It's not using very much information. All we're using is the signs and not the sizes of anything. But that's the sign test.